Bismillahirrahmanirrahim. Assalamu alaikum warahmatullahi wabarakatuh. This is Dr. Amini Abdul Fattah, lecturer of Histology and Cell Biology, Mansoura Faculty of Medicine. And today, inshallah, we will discuss together the histology of the heart and the blood vessels. Our objectives today will be to describe the structure of the wall of the heart, to mention general structure of the wall of blood vessels, enumerate types of blood vessels according to their size, know characters of the wall of aorta, inferior vena cava, medium-sized artery and vein, and lastly to compare different types of blood capillaries. Let's start by mentioning the components of the cardiovascular system. So here we can divide the cardiovascular system into two main parts: the heart, which is considered the pump of the blood, and the blood vessels, which are the pathways inside which the blood flows. And blood vessels could be subdivided according to the blood inside, whether it is oxygenated or deoxygenated blood, into arteries, and these are the blood vessels contain oxygenated blood; veins, and these are the vessels that contain deoxygenated blood; and lastly we have the very narrow vessels or small vessels connecting arteries with veins, what we call AV connection or arteriovenous connection. So these are totally the components of the cardiovascular system. Here we have this diagram illustrating what we mentioned now. Here is the heart, with the pump of the blood, as I mentioned, pumping blood into the blood vessels, and all of these are the blood vessels branching. All of these are blood vessels, the red representing the arteries contain oxygenated blood, and the blue representing the veins contain deoxygenated blood. Let's start by the first part, which is the heart. To define the heart is a muscular organ which contracts rhythmically, pumping the blood through the circulatory system. This means that it is a pump of blood, it is the chambers, or its chamber contain blood, contraction of this chamber pushing the blood into the blood vessels. So here we have the components of the heart. Anatomically, we can divide the heart into two thin atria. Here are the two atria, right and left atrium, and two thick ventricles. This is the left ventricle and this is the right one. So here we have four chambers inside the heart, two thin atria and two thick ventricles. Histologically, if we have a section of the wall of the heart under the light microscope to describe it, the wall of the heart is formed mainly of three main layers. These layers are arranged from outside as we go in. The first one is called epicardium, and this is the outermost layer of the wall. The middle layer is the myocardium, here is the myocardium, and the most inner one lining the heart chambers from inside, this is called the endocardium. So again, we have three layers forming together the wall of the heart under the light microscope. The first and the outermost one is called epicardium. The middle one, which is the thickest zone as you see here, it is the myocardium, and the inner lining of the chambers is the endocardium. The whole heart is covered by a sac. This sac or double-walled sac is called the pericardium. So the pericardium is the outer covering of the heart from outside. It is not one of the layers of the wall, but it's the covering of the heart from outside. Here is the diagram for what we mentioned now. Here we have the layers forming the wall of the heart. The outer covering is the pericardium. The first layer and the outermost again is epicardium, middle myocardium, and inner endocardium. Let's start by discussing the pericardium. As we mentioned, it is the outer covering. It is a serous sac which surrounds the heart. So it is the outer covering of the heart from outside. Regarding its structure, pericardium is formed of two layers. The outer one called parietal layer, this one, and the inner one is the visceral layer, and this is the visceral one. And in between we have a cavity. This is called pericardial sac. or pericardial space. So again, regarding the structure of pericardium, it is double-walled sac. Double wall means it has two layers. The outer is the parietal layer, the inner is the visceral layer, and in between we have a space. This space contains a little amount of lubricant fluid. Lubricant means it facilitates the movement of the two layers during the contraction and relaxation of the heart, so it prevents the friction between the two layers. This is regarding the pericardium structure. Let's start by the first layer of the wall. The outermost, as I mentioned, is the epicardium. Here is the diagram for the wall of the heart, and here is the epicardial layer. It is the outermost one, so it is just next to the pericardium. And actually, this layer is representing the visceral layer of pericardium. So it is the first layer of the wall, and at the same time, it is the visceral pericardium. It is the visceral layer of pericardium. Microscopically, this layer is formed of simple squamous epithelium, and here the epithelium. It is the single layer of flat cells with flat nuclei covering its outer part, underlaid by a layer of connective tissue. As we mentioned before, mostly epithelium is underlaid by connective tissue in any part of the body. So here also we have a simple squamous epithelial layer, flat cells with flat nuclei, underlaid by a layer of connective tissue. This layer is characterized by being rich in fat cells, together with the presence of the coronaries, the blood vessels supplying the wall of the heart itself. So these are the coronary blood vessels. They are the blood vessels supply the wall of the heart with the blood and oxygen and nutrients. These are present in the connective tissue layer of epicardium. So again, the first layer of the wall of the heart is called epicardium. This is the outermost one. Here, this is the epicardium. Actually, as we mentioned, it represents the visceral pericardium. So both are the same. Visceral pericardium is the same as epicardium. This layer histologically is formed of two components. First is epithelium, which is simple squamous epithelium, underlaid by a layer of connective tissue, contain fat cells, and coronary blood vessels, which are supplying the heart. Let's shift to the second layer. The second or the middle layer of the wall of the heart is called myocardium. Here is the myocardium. It is the middle layer regarding its orientation and its relationship to the other layers. Comparing the thickness of myocardium with the other layers, it is the thickest one. So it is much thicker in general, in comparison with epicardium and endocardium, and it's much thicker in ventricles more than atrium. So the myocardium is not with fixed thickness. The thickness of myocardium differ according to the chamber. So in atrium, it is thin. In ventricle, it is thicker. And it is more and more thicker in the left ventricle more than the right one. It's okay? This is regarding its thickness. Regarding its histological structure, actually it is called myocardium, and the prefix myo denotes muscle. So this layer is mainly formed of cardiac muscle fibers. These are the main type of muscles present in the heart. They are specific type, cardiac muscle fibers. They are present in the myocardium in a spirally arranged manner around each chamber. So this is the main structure of myocardium. It is formed of cardiac muscle fibers. These cardiac muscle fibers are separated by thin parts of loose connective tissue, contain some blood vessels for its nutrition and support. So here is the structure of myocardium in general. It is mainly cardiac muscle fibers, and in between we have loose connective tissue. Let's try to mention in short what are the characteristics of cardiac muscle fiber as a type of muscle when we compare it with the skeletal or the smooth type. What are the characteristics of this type? Cardiac muscle fibers are formed of short cylindrical cells with extensive branching and anastomosing. What does this mean? Simply, the cardiac muscle fiber, this is one fiber, for example. This fiber is formed of multiple cells. So these are cells arranged side by side. It forms one fiber. These cells are cylindrical in shape, And the fiber as a whole can branch and reanastomose, and so. So here we have extensive branching and anastomosis of the cardiac muscle fiber. This is the first criteria of this type. This muscle also are joined together by cell junctions, type of communication that adhere the cell together, what we call intercalated discs. So this type of fibers is characterized by being joined together. They are adherent to each other by a type of cell junction called intercalated discs. Here is the shape of the fibers under the light microscope, stained with H&E. Here are the cardiac muscle fibers. Each is formed of multiple cells, and this is the nucleus of the cells. So here is intercalated disc separating the cells from each other. This is the site of cell junction, and at the same time, it is the site of separation, the site at which one cell ends and another cell starts. Here is the intercalated discs. Third property of this type of fibers, it is striated. And this striation is characteristic for both cardiac and skeletal, but it's absent in the smooth type. So here in the cardiac muscle fiber, they are striated fibers. Here we can see, this is a photomicrograph for the cardiac muscle fibers stained with a special stain called phosphotungistic acid. This is very characteristic to clearly manifest these striations of the fiber. So here you can clearly see that the fiber are striated fibers. These are the striations characteristic for both cardiac and skeletal muscle fibers. Regarding the cells, each cell has large oval central nucleus and may be binucleated in some cells. Some cells contain only one nucleus, others contain both or binucleated or two nuclei. Regarding the cytoplasm of cardiac muscle fiber is acidophilic and granular. So it's acidophilic and granular due to the presence of numerous mitochondria in this type. Here is a photomicrograph for the cardiac muscle fibers, and here you can see again, each fiber is formed of multiple cells. Here are the cells. This is one cell, and this is the next one. Here is the separators or the sites of cell junction, what we call intercalated disc. These are the branching of the fibers. So here you can see that this one is branched. This is the branching of the fibers. Here are the nuclei. They are rounded or oval, central in position. And as we mentioned, it may be one, maybe two per cell. And here are the intercalated discs that are the sites of cell junction between adjacent cells. The innermost layer, or the third layer of the wall, is the endocardium. And it is called endo, denoting its side. Endo means inside. So it is the inner layer. It is a layer just in direct contact with the blood present inside these chambers. So here is the endocardium, and here is the cavity of the heart from inside containing blood. It lines the chambers of the heart, so it lines the inner surface of the both atria and ventricles, and at the same time they are reflected to cover the surface of the valves separating the atria from the ventricles. This is regarding the site of endocardium. Microscopically, endocardium is formed of simple squamous endothelial layer. The first layer of the endocardium is similar to what we mentioned in the first layer of epicardium. Both are lined or covered there by a layer of flat cells with flat nuclei, simple squamous epithelium. So the first layer of the endocardium in direct contact with the blood is simple squamous epithelium. And here, classically, they are called endothelium, characterizing epithelial lining of heart and blood vessels. So the epithelium lining the heart and all blood vessels is specifically named endothelium. So the first layer of endothelium again, the first layer of endocardium is simple squamous endothelial layer, which is flat cells with flat nuclei lining the chambers. Again, underlined by connective tissue. This is in general. So here it is also underlined by subendothelial. Sub means under. So subendothelial layer of connective tissue. This layer is characterized by being rich in or having or containing elastic fibers, collagen fibers, and some smooth muscle fibers. Here is the layer just directly under the endothelium. It is a subendothelial connective tissue containing what we mentioned regarding the fibers and some smooth muscle fibers. The third layer of the endocardium is called subendocardial layer. And actually, this subendocardial layer is the separator between endocardium and myocardium. So it's described by the word subendocardium. It is a layer of endocardium itself, but it is the site of separation between endocardium and the connective tissue surrounding the myocardium. Or it is in continuation with the connective tissue surrounding myocardium. Here in this part, or the subendocardial layer, it's also loose connective tissue, contain blood vessels, and in addition, it contains specialized or modified cardiac muscle fiber called Purkinje fibers. Here are the Purkinje fibers. So these fibers are present in the subendocardial layer of endocardium. These fibers are very characteristic and are specialized in conduction of the nerve impulse inside the heart. So it's considered part of the conducting system of the heart. So Purkinje fibers are present in subendocardial layer. Again, this layer is in continuation or is continuous with connective tissue of myocardium. So here is the myocardium surrounded by a connective tissue, which is in continuation with the subendocardial layer. So again, regarding endocardium, it is formed of 3 layers. First one, the most inner, is endothelium, simple squamous epithelium, underlined by subendothelial connective tissue, underlined more by subendocardial connective tissue. Subendothelial contain collagen, elastic, and some smooth muscles. Subendocardial contain Purkinje fibers. These are very, very important fibers representing part of the conducting system of the heart. What are the characteristics of these fibers? I mentioned that they are modified cardiac. What are the modifications that occur in the Purkinje fibers, differentiating them from other cardiac muscle fibers? Actually, these Purkinje fibers are specialized cardiac muscle fibers characterized by: number one, they are larger in size. So when we compare the size of Purkinje fiber with the size of cardiac muscle fibers, they are larger in size. They are larger than the ordinary contractile cardiac muscle fibers. Second point, they have large rounded nuclei. So here the nucleus is rounded. It's mostly oval in the cardiac muscle, but here in the Purkinje, they are large rounded nuclei. Regarding the staining, if we examine the cytoplasm of Purkinje compared with the cytoplasm of ordinary cardiac, cytoplasm of Purkinje is pale stained. It appears paler in coloration or paler in staining with H&E compared with the cytoplasm of cardiac muscle fiber. What is the cause of this paleness? Why they are appearing pale compared with other cardiac muscle? Because of 2 reasons. The first one is that these fibers contain few myofibrils and they are peripherally situated. These myofibrils are the components of the cardiac muscle fiber. The main component responsible for contractility of the cardiac muscle fiber is a small myofibrils. Here, they are modified because they are conducting. They are not contractile fibers. So here, there is no need for much myofibrils. They are few in number compared with the cardiac muscles, and these are the site for presence of proteins and mitochondria and all other organelles present in the cardiac muscle fibers. Here in the Purkinje fiber, they are not contractile, so there is no need for presence of myofibrils. They are few and peripherally situated. In addition, these cells, or the cytoplasm of these cells, is characterized by having much glycogen. And this glycogen dissolved during preparation of the section, during staining, making the cytoplasm pale, stained, or vacuolated. So again, Purkinje fibers, in order to be compared or differentiated from other cardiac muscle fibers, these fibers are larger in diameter, larger in size. They have a large rounded nuclei, and its cytoplasm is characterized by being paler, pale acidophilic compared with the cardiac muscle fibers. The paleness is due to the few myofibrils together with increased amount of glycogen present in its cytoplasm. What is the function of these fibers? I think we mentioned that before. They are part of the conducting system of the heart. So here they are specialized in conduction of electrical impulses rapidly through the heart it allows the heart to contract as one unit. So this is part of the conducting system, conducting electrical impulse. So again, they are not contractile fibers. They are considered to some extent similar to the action of neurons. They are conducting the electrical impulses to the heart muscle. This is regarding Purkinje fibers. It's a site in the subendocardial layer. Its characters, large with rounded nuclei and pale stained cytoplasm. And lastly, its function is to conduct electrical impulse through the heart wall. Here is a section for the whole heart thickness, or the wall of the heart as a whole. Here is the section. The first layer, the outermost, is epicardium. The middle one, thickest zone formed of cardiac muscle fibers, which is the myocardium. And the most inner one, lining the heart from inside and in contact with the blood, which is endocardium. Here is another section, but it is longitudinal section for the heart wall, section in the left atrium with the ventricle. So this thickness represents the atrial wall, and this thickness represents the ventricular wall. So here is the atrium, and here is the ventricle. Here are the three layers we mentioned: epicardium, outermost one. Next, myocardium, thickest one, and thin endocardium, represented by the epithelium and the underlying connective tissue. Here is the inner layer. Here is the valve. We mentioned that endocardium cover the valve. Here is the mitral valve separating the cavity of the atrium, the left atrium, from the cavity of the left ventricle, and it is covered by the endocardium. The second part of our lecture today, we will discuss the blood vessels. So the blood vessels are the vessels which carry the blood to and from tissues of the body. So they are the pathways of the blood, where the blood goes and flows to reach the tissues, supplying them and taking waste product from the tissues to reach the sites for exchange. So vessel wall, if we have a section of any vessel wall in general, whatever its type, the vessel wall is formed of three layers. Here is the diagram for one of the vessels, whatever its type again. So these are general scheme for the wall of blood vessels. It is formed of three layers. The most inner one is called tunica intima. This is the tunica intima in direct contact with the blood inside. The middle one is called tunica media. Media is middle. Here is the tunica media. And the outermost layer is the tunica adventitia, the outermost layer of the vessel wall. So again, if we have a section of any vessel, whether it is artery, it is vein, any vessel of these two types is mainly formed of three layers. From inside, as we go out, tunica intima, tunica media, and lastly, tunica adventitia. Also in general, tunica intima is formed of endothelium. It is the most inner layer of tunica intima in direct contact with the blood again. So it is very similar to what we mentioned in the endocardium. The first layer of endocardium is endothelium, and the first layer of tunica intima of blood vessel is endothelium. It is simple squamous epithelial cells, flat cells with flat nuclei, lining the vessel from inside. And they are resting on basal lamina or basement membrane. Here is the endothelial layer, underlined by, as we mentioned before, connective tissue, subendothelial connective tissue. Here, the subendothelial connective tissue is a layer of loose connective tissue underlying the epithelium. The outermost layer of tunica intima is called internal elastic lamina, this one. This internal elastic lamina is present in tunica intima of arteries only. So if we mention the wall of a vein, we will not mention the presence of internal elastic lamina. It is only present in arteries. So this is to be noted. Internal elastic lamina is only seen in the wall of arteries only, not in the veins. And this layer is formed of fenestrated bands of elastic fibers separating intima from the next layer, which is the media. So again, the first layer of the vessel wall, any vessel, is formed of 2 or 3 layers, because we mentioned that internal elastic lamina is only in arteries, so it's absent in veins. The 3 layers are endothelium, subendothelial connective tissue, and internal elastic lamina only in arteries. These are the 3 layers forming tunica intima. Second layer of the wall of vessel is called tunica media. And it is media, so it is metal. This layer is mainly formed of smooth muscle fibers. They are circularly arranged around the vessel wall. Here is the media. It is formed of circularly arranged smooth muscle fibers, in addition to elastic fibers. Also, they are only present in arteries. So please remember that. The word elastic is not mentioned except when we mention the structure of arteries. If we mention structure of any vein, we will remove the word elastic from the whole vessel wall or the whole vein structure. So the word elastic, internal elastic lamina, elastic fibers in the media, elastic fibers in the adventitia. Elastic is coincident with the arteries only. They are only present in arteries and absent in veins in general. So any structure or any part of the vessel wall contain elastic fiber is only confined to arteries and absent in veins. So again, tunica media is mainly formed of smooth muscle fibers together with some elastic fibers in arteries only. Also, in addition, we have another 2 types of connective tissue fibers, collagen and reticular fibers. And in addition, we have external elastic lamina only present in arteries. Yes, that's it. Elastic arteries. External elastic lamina present mainly in large muscular arteries, and it is a separator between media and adventitia. So here we have internal elastic lamina separating intima from media, and external elastic lamina separating media from adventitia. Also, it's only present in arteries, mainly the large muscular arteries. This is the structure of tunica media. The outermost layer of the wall of any vessel is tunica adventitia. And the word adventitia mostly denoting connective tissue. So here it is a tunica externa or adventitia, and here is also tunica interna or tunica intima. Both are the same. Tunica adventitia is formed of collagen and elastic fibers, so it's formed of connective tissue contain collagen and elastic fibers. And in addition, it contains small blood vessels that supply the vessel wall. So here we mentioned that this is a blood vessel, right? Yes. This is the wall of the blood vessel. Yes. This wall needs nutrition. This wall needs oxygen and nutrients to live. These cells need oxygen and need nutrients. So they need small blood vessels to supply the blood vessel. Yes. These are called vasa vasorum. So vasa vasorum, they are the vessels of the vessels, the small vessels supplying the wall of blood vessels. Here is the tunica adventitia. So again, in tunica adventitia, the outermost layer, it contains mainly collagen and elastic. And again, elastic here, we will be mentioned only in arteries. We will remove elastic when we mention tunica adventitia of veins. And it contains small blood vessels to supply this wall, these cells. They are called the vasa vasorum. Structure of vessels differ according to its type and size. So the structure we mentioned now, the 3 layers, intima, media, and adventitia, will differ according to the type. It differs in arteries from veins, and according to size, it differs between large artery, medium-sized, or arteriole. Also differ between IVC, for example, inferior vena cava as large vein, and medium-sized vein and small venules. So these 2 points are important to be mentioned because they are a characteristic for that each vessel have its own structure. The 3 layers are present, but with different criteria. So we will classify the arteries into 3 types: large arteries like the aorta, medium-sized arteries like the muscular arteries, and small arteries called arterioles. On the other hand, we will classify the veins with the same manner. So we have large veins like the IVC, inferior vena cava, medium-sized veins and small veins called venules. As we mentioned, the structure will differ according to the type, according to the size in each type. Here is a diagram clarifying or manifesting the different types of vessels as I mentioned now. Here are the 3 layers we mentioned: intima, media, and adventitia, forming the wall of the vessel. Here is the arteries, and here are the veins. In this part, here is one of the large arteries, the aorta, and here is the smaller muscular artery, or the medium size, and here is the smallest arteriole, smallest artery. On the other hand, we have large vein like the IVC, we have medium-sized veins and smaller venules. In between, we have the capillaries, or the AV connection connecting the arterial side with the venous side. Let's start by the structure of the large vessels, the large artery versus the large vein. What are the points of similarities and what are the points of differences? Here is a table summarized to us the structure of artery, large artery represented by the aorta, and one of the large veins represented by IVC. And here we try to compare the structure of the 2 vessels regarding general characters, regarding the 3 layers of the wall: the intima, the media, and the adventitia. Let's start by the first point, general characters. Aorta as a large artery is characterized by having thick wall and wide lumen. So here we have thick wall and wide lumen characteristic for aorta. On the other hand, IVC as a large vein, it has thin wall and very wide but collapsed. Collapsed means it is not wide as we see here. It is a diminished lumen or narrower, and the vessel is collapsed, need to be closed. And here, this vessel, its lumen have many valves controlling the passage of blood inside. So again, the first point in comparison between aorta and inferior vena cava is the general characters. Aorta is characterized by having thick wall and wide lumen. IVC is characterized by having thin wall, wide collapsed lumen. Regarding the layers, the first inner one is intima, and intima in aorta is thick. Thick in artery, thin in vein. Media is thick in artery, maybe very thick in aorta, thin in vein. Adventitia is thin in artery, thick in vein. So here we can notice the difference in the thickness of each layer. In comparison, arteries in general, aorta specifically, have thick intima, very thick media, and thin adventitia. Veins in general, and specifically IVC, have thin intima, thin media, and very thick adventitia. Very for the vessel, large vessels. But in general, when we mention the structure of vessels, not the large, we will remove the word very. So it will be thick only in medium-sized artery. It will be thick only in medium-sized vein. Here is the difference in the thickness of each layer. Regarding the structure, intima of aorta is formed of endothelium and subendothelial layer rich in elastic fibers. So remember that elastic means artery. Aorta is large artery, so it contains numerous elastic fibers. It is rich in elastic fibers. And internal elastic lamina, almost all present. It's present here in the aorta, but it's not clearly identified or seen. It's okay, but it's present. It is rich in elastic fiber in general, the wall as a whole. So it is rich in elastic fibers in the subendothelial layer, and internal elastic lamina is present. On the other hand, IVC have thin intima, only formed of connective tissue with collagen fibers. No elastic fibers are present at all. And at the same, internal elastic lamina is also absent. So here we will remove any word with elastic, will be confined to aorta or to arteries in general, including aorta, and absent in the veins, including IVC. The second layer of the wall is tunica media. We mentioned that it is very thick in aorta, thin in inferior vena cava. It represents the main thickness of the whole wall. So the thick wall is mainly thick due to very thick media. Regarding its structure, it is formed of fenestrated elastic laminae, numerous elastic fibers, stretching elastic fibers, together with smooth muscle fibers or smooth muscle cells, collagen fibers, reticular fibers, and ground substance. So these are the components of the media of the aorta, mainly rich in elastic fibers, together with smooth muscle, collagen, reticular, and ground substance. On the other hand, inferior vena cava has thin media, and this media is only formed of smooth muscle fibers. It may contain some collagen fibers, but there is complete absence of elastic fibers. No elastic fibers are present in the media of inferior vena cava. The third layer of the wall is the tunica adventitia. As we mentioned, regarding its thickness, it is relatively thin in aorta compared with the other layers, and very thick in inferior vena cava compared with other layers. In aorta, it contains collagen and again, elastic fibers, together with what we mentioned, the vessel, the vada vasora. In the inferior vena cava, it is very thick. And this thickness is mainly due to presence of connective tissue with collagen and vasa vasora, but in addition, we have groups or bundles of longitudinally oriented smooth muscle fibers. So here we have, in addition to the connective tissue of the adventitia, we have smooth muscle fibers in the adventitia of inferior vena cava. This is very characteristic for inferior vena cava. In any other vein other than inferior vena cava, there is no smooth muscles in the adventitia. So this point is very characteristic for inferior vena cava. It contains in its adventitia collagen, connective tissue with its components, collagen and reticular fibers, but in addition we have longitudinally oriented bundles of smooth muscle fibers. So here we gather the differences between aorta and inferior vena cava as two examples of the large artery compared with the large vein. Here are the two diagrams for the two vessels. So here we have one vessel have intima, thick media, thin adventitia, compared with another one having thin intima, thin media, and thick adventitia. So this is mostly the aorta, this one, and this is mostly inferior vena cava. Here we have the intima and the evident thick media formed of elastic fibers and smooth muscles, and the adventitia, which is thin. Here we have thin media, thin intima, thin media with smooth muscle fibers only, with no elastic fibers, and thick adventitia, or very thick, having smooth muscle bundles. Here are the bundles of smooth muscle characteristic for the wall of inferior vena cava. Here are the two vessels under the light microscope. So here is the thickness of aorta compared with the thickness of inferior vena cava. Here are the three layers forming the wall: intima, media, and adventitia. And here are the three layers forming the wall of inferior vena cava: thin intima, thin media, and thick adventitia. Here are the bundles of smooth muscles present in the adventitia again of inferior vena cava of the adventitia of inferior vena cava. So here is a section of aorta, and here is a section of inferior vena cava. Let's shift to the second category according to the size, which is medium sized. So here we also compare medium sized artery with medium sized vein. Here is another table summarizing the differences between medium sized artery, or what we call sometimes muscular artery, compared with medium sized vein. We will compare with the same 4 points. So here we will mention general characters, then we will mention the 3 layers and differences between. General structure or general characters of artery have thick wall and narrow lumen. So in general, all arteries have thick wall. All arteries except the aorta have narrow lumen, because the aorta is the largest artery, so we cannot describe it with narrow lumen. The vessel that pushes the blood to the whole body. So it is a must to have wide lumen to accommodate the blood coming from the heart. But other than the aorta, all the arteries or other arteries have thick wall and narrow lumen. On the other hand, regarding the vein, medium-sized vein have thin wall and wide collapsed lumen, similar to what we mentioned in the inferior vena cava. It has thin wall and wide collapsed lumen. Regarding the valves are confined to veins. So there is no valves in the lumen of any artery, but they could be present or they are seen in the lumen of the veins, whether inferior vena cava or medium-sized veins. Both have valves inside. Let's shift to the layers. Intima, media, and adventitia, and differences between. Regarding the thickness, it is the same manner as we mentioned in the large vessels. So, in medium-sized artery, we have thick intima, thick media, and thin adventitia. In medium-sized vein, we have thin intima, thin media, and thick adventitia. This is regarding the difference in the thickness of the layers compared with each other. In the artery, we have thick media, formed of what we mentioned before, the endothelium with endothelial connective tissue contain collagen and elastic fibers, and here we have well-developed internal elastic lamina. So this is very characteristic for medium-sized muscular artery. It contains or it has well-developed, clearly seen internal elastic lamina. On the other hand, in the vein, intima is thin and no elastic fibers at all are present and no internal elastic lamina is present. It is absent in the vein. Regarding the media is thick in the artery and it is mainly formed of smooth muscle fiber together with elastic fibers. So both are present in the muscular artery. It is formed of smooth muscles with elastic fibers, and external elastic lamina may be present. It's present in some medium-sized arteries, absent in others. So it's not specific for the medium-sized arteries in general. It's present in some of them and absent in others. Regarding media of vein, it is thin. It is formed only of smooth muscle fibers. No elastic fibers are present in the media of vein, and no external elastic lamina is present. It is absent also. So again, remember that any word having elastic is only present in artery and absent in vein. Regarding the third one, the third layer, tunica adventitia, it is thinner in the artery and thinner than media and intima when we compare the thickness of the three layers, and contain elastic and collagen fibers together with the vada vasorum. In the veins, medium-sized vein is thick and it's only formed of collagen fibers. No smooth muscles are present. Remember that the presence of smooth muscle in the adventitia is characteristic for inferior vena cava only. They are not present in any other vein. So here the media, the adventitia is thick, but it's only formed of collagen fibers. Connective tissue contain collagen fibers and vasa vasorum. No elastic fibers and no smooth muscle fibers. This is regarding the medium-sized artery compared with medium-sized vein. Here is the section of the two vessels under the light microscope. So here we can see this is a section of artery compared with this is one of vein. Here we have thick wall and narrow lumen compared with thin wall and wider lumen of the vein. This is regarding the difference in the general characters. Here's a diagram for the layers forming the vessel. So here we have the intima. It is thick intima, thick media in artery, and thin adventitia, while here we have thin intima, thin media, and thick adventitia. Under the light microscope, if we have a section of both vessels, so here is the thickness of the artery. It is thicker compared with the thickness of the vessel, with the vein. Here are the three layers, intima, thick, media, thick, and thin adventitia. Here is the reverse. We have thin intima, thin media, and thicker adventitia. The third component of our lecture today will be the AV connection, or the third type of vessels. We mentioned the arteries and the veins with its different sizes. The last component of the blood vessels is the AV connection, what we call arteriovenous connections. The AV connections are the small vessels which connect. From its name, it is AV connection. So they are connecting arteries with veins. They are the vessels which connect the arterial side with the venous side. This is the definition of the AV connection. Here we have one artery and one vein, and the connecting vessels connecting arteries with veins are what we call AV connection. These AV connections include blood capillaries, blood sinusoids, and arteriovenous shunts. So these are the three types of the AV connection. It may be blood capillaries, wider capillaries called blood sinusoids, and the AV shunt, which is a direct connection between artery and vein without passing through the capillaries. This is the AV shunt. This is a vessel connecting the artery with the vein directly without passing through the capillaries. This is what we call the AV shunt. So here we have mainly two examples. We will mention in details what are the blood capillaries and what are the blood sinusoids. The first one of the AV connection is the blood capillaries. And to define these capillaries, they are thin-walled, tubular blood channels. These are the criteria of the capillaries. It is tubular blood channel, which have thin wall, compared to the capillary wall with the other vessel wall is very thin. When we compare it with the arteries or veins, they have very thin wall. These capillaries conduct the blood from terminal arteriole to terminal venule. So here is the site. The capillary is present between a very small artery called arteriole and very small vein called venules. And its diameter ranging from 8 to 10 micron. This is the range of the diameter of the blood capillaries. Regarding its structure under the light microscope, the blood capillary is mainly formed of two layers. The innermost one is endothelium. Again, endothelium, yes. We mentioned that all the vessels containing blood, the blood is in direct contact with a simple squamous epithelium called endothelium. Whatever the blood is present, endothelium is present. So here, the innermost layer of the capillary is also endothelium, simple squamous epithelial layer. Here is the single layer of flat cells lining the capillaries from inside. Underlined by the basal lamina, here is the basal lamina or the basement membrane surrounding the endothelium or the epithelium. In between, we have a pericyte. This is a cell present in between the endothelium and its basal lamina. This is called the pericyte. So the wall as a whole is endothelium underlined by basal lamina. In between, we have a cell called the pericyte. This cell is considered the primitive or undifferentiated cell. This is the structure of the wall of the capillaries. According to the type of the wall and presence or absence of holes in this wall, we will classify the capillaries into three types. The first one is called continuous capillary. The second one is called fenestrated capillary. And the third type is called discontinuous capillaries, or what we call in other name, blood sinusoids. So blood sinusoids are the discontinuous type of the blood capillaries. So again, you will classify the capillaries into three groups, depending on presence or absence of fenestry, holes in its wall. The first type, from its name, it is called the continuous. So there is holes, or holes are present or absent in this type. Mostly it is called the continuous due to absence of holes. There is no holes at all present in this type. The second type is called the fenestrated. Fenestry is the hole. So this type is mostly having holes in its wall. The last type, or the third type, is called discontinuous. So this type, from its name, discontinuous, means its wall is discontinuous. It's not following each other. It is not continuous layer. It has many holes also in its wall. But we will mention what is the difference between fenestrated and discontinuous. So these are the three names for the three types of capillaries: continuous, fenestrated, and discontinuous. What are the characters of each type? Regarding the first one, continuous type, this type is characterized by having no fenestry at all. So no holes are present in the wall of continuous capillaries. Here is the shape or the diagram for the vessel wall, the capillary wall. Here we have continuous endothelium. So the cells are intact cell with no fenestry at all. And the basement membrane or the basal lamina is also continuous with no holes present in it. Both layers of the capillaries are continuous layers, continuous endothelium and continuous basal lamina. This is the first type. Let's shift to the second type. It is called fenestrated, and it is called fenestrated due to presence of fenestry, holes in its wall. Here we have the shape of fenestrated type. This type have fenestrated endothelial cell, so the cell itself, the cell lining or the endothelial cells have fenestry in its wall. The wall of the cell is discontinuous. It has fenestry or opening in the wall of the endothelial cell itself. But on the other hand, the basal lamina surrounding it is continuous. So the holes here are considered to be closed by the continuous basal lamina. So again, the second type of capillaries is called fenestrated. And from its name, fenestrated means it contains fenestry. But what is the site of fenestry? It's only present in endothelial cells. Here are the capillaries. Here are the endothelial, and here are the fenestry or the holes present in its wall. And on the other hand, the other layer of the wall, which is the basal lamina, is continuous layer. It have no holes. This is the second type. Third type of capillaries is called discontinuous, or again, we call it blood sinusoids. This type is characterized by having multiple fenestry in the endothelium. So in this point, it's similar to fenestrated. The endothelium have fenestry. Here you can see it. These are the holes present in the endothelial cells. But at the same time, the basal lamina surrounding it is also discontinuous. So here we have holes in both endothelial cells and the basal lamina surrounding it. This is the main difference between discontinuous and fenestrated. In fenestrated type, we have continuous basal lamina surrounding fenestrated endothelium, but here we have both discontinuous. Endothelium have fenestry and basal lamina is discontinuous. This type is mostly characterized by having enlarged diameter, so that the diameter of the sinusoids is mostly larger than other capillaries. It may be from 30 to 40 micron in diameter, compared with 10 micron of other capillaries. And this type is also characterized by presence of macrophages surrounding its wall from outside. So the macrophages are present outside its wall here in this area. Macrophages are present outside the sinusoidal wall. These are two characters for the blood sinusoids and not present in the capillaries. In general, in other capillaries, the enlarged diameter is characteristic for sinusoid. They have wider diameter. And the presence of macrophages surrounding its wall is also characteristic for the sinusoids and not present in other types of capillaries. Let's know some examples or sites. Where can I find continuous type in the body? Where can I find fenestrated type? And where can I find the blood sinusoid? Regarding this type, it could be found in the muscle tissue, connective tissue vessels, and in the nervous tissue vessels. So in the capillaries of the nervous tissue, it's continuous type. Capillaries of the muscles, it's continuous type. And the capillaries present in the connective tissue is continuous type. Regarding the fenestrated type, this type is mainly found in the kidney, capillaries of the kidney, or the glomeruli specifically, intestine, and endocrine glands. These three types, or these three sites for the fenestrated capillaries in the body. Regarding the blood sinusoids, we can find it in the bone marrow, in the spleen, in the liver, and the endocrine glands. So these are the sites of the presence of blood sinusoid in the body. So here, we gather the information about the capillaries in this table. We differentiate the three types according to the characters, whether there is fenestry or not in the wall. And regarding the sites, examples for the sites of presence of each type in the body. This diagram summarizes what we mentioned now. So here we can see continuous capillary. Why continuous? Continuous endothelium and continuous basal lamina. In the fenestrated type, we have fenestry, many holes in the endothelium, but we are still having continuous basal lamina. In the sinusoidal type, we have fenestry in the endothelium and discontinuous basal lamina. What are the functions of the capillaries? Capillaries are very thin vessels present in the body, but they are performing very important functions. The first and the most common one for the capillaries in general is the exchange. selective exchange of materials between the blood and tissues. So here are the sites of exchanging materials. Capillaries give the tissue oxygen and nutrients and take waste products from the tissue to the blood. So these are the first and most important and most famous function of capillaries in general. So the capillaries all over the body is important for selective exchange of materials between the blood and the tissues. Specifically, function of blood sinusoids. So blood sinusoids have separate functions other than the exchange. The blood sinusoids we mentioned present in the bone marrow, present in the spleen, in the liver, they have specific function in each site present in. In the bone marrow, for example, these blood sinusoids are important for migration of blood cells to the general circulation. You know that the bone marrow is a factory for tens of blood cells. So how can these cells reach the circulation? Through presence of large vessels or large capillaries, sinusoids, which allow the newly formed cells to enter the circulation. So here is a function of the blood sinusoids in the bone marrow. It allows the migration of the newly formed blood cells in the bone marrow to reach or to enter the general circulation. In the spleen, the blood sinusoids serve as a storage site for blood. So blood sinusoids of the spleen contain numerous blood sinusoids full of blood, and this is considered a store for the blood in the body. At the same time, these sinusoids are surrounded by macrophages. We mentioned that before. So these macrophages in the spleen provide a very important function, which is filtration of the blood. The blood is passing through the sinusoids, filtered by the macrophages outside its wall, removing any foreign bodies, or bacteria or dead RBCs. Dead RBCs are removed also through this filtration process from the bloodstream. So again, in the spleen, the blood sinusoids have two important functions: is to store the blood for the time of need. For example, in hemorrhage, the spleen contracts to push the blood inside, which is stored inside, to the general circulation. And at the same time, it filters the blood passing through the sinusoids by the presence of the macrophages surrounding its wall. In the liver, the blood sinusoids allow the blood to come into contact with the hepatocytes. And actually, hepatocytes perform many functions. One of them is, for example, the formation of lipoproteins, or the proteins that passing in the blood. Formation of these proteins will pour into the blood through the presence of the capillaries. So the sinusoids in the liver. So here the blood is in the sinusoids is important to become in contact with the hepatocytes, which perform many functions concerned with the blood. Lastly, in the endocrine glands have blood sinusoids, and these sinusoids allow the release of hormones to the blood. So here, the blood sinusoids in the endocrine glands represent one of the alternatives for the absence of the duct. There is no duct in the endocrine glands. So how the hormone will reach its target site of action? Through the bloodstream. The blood is poured into the blood. The hormones synthesized by endocrine glands are released into the blood through the presence of the sinusoids to reach its target site of action. So here are the specific functions for the blood sinusoids. We generalize the function of capillaries in the exchange function. But in the blood sinusoids, we mention specifically function of sinusoid in each site. Now I finished my lecture. I hope that it is clear for all of you, and let's shift to some questions to examine yourself or ask yourself and mention and test yourself for understanding the lecture. First one, which is the character of cardiac muscle fiber. Which one of them is considered the character of cardiac muscle? Yes, the answer is composed of chain of cells. This is the appropriate right answer. Second question, internal elastic lamina is well developed and which one of them having well developed internal elastic lamina? We mentioned that it is muscular arteries. Yes, that's right. The third question, which is the character of large vein? Which one of them is the correct answer regarding the large vein? Yes, have thin wall and wide lumen. This is the appropriate answer for the description or the character of a large vein. finally, thank you for all of you. I hope that the lecture is clear and understandable, and wishing you good luck, and thank you again. Assalamu alaikum.